Hi, this is Anna Doblas. Today's video is about solving some multi-choice questions for module number 4, which topic is Fourier optics. So the first question that it's telling us is it's a true-false question, and it's telling us like if the diffraction patterns of an object are a scale copy of the Fourier transform of the object amplitude t under the Fraunhofer approximation. So basically what we know is that they are telling us that here we have our transmittance that is gonna be t, and then we are observing and the Fraunhofer approximation, and we know to know what is gonna be the output, right? So we know that the resultant, like the light propagating a distance c, is our object transmittance convolved with the free propagation kernel j lambda c, and now here we have our spherical waveform expressed in paraxial approximation, right? And this is a 2D convolution, so we can definitely work it out, writing the convolution in integral form. So here we have x squared plus y squared, and now here we have our integral that is going from minus infinity to infinity of what? Of t alpha beta, and then we have our complex exponential, the exponential of j k to c, where inside what we're gonna have is our x minus alpha and everything is squared, and we have exactly the same for our vertical component. So here is gonna be y minus beta, and the integral is going into the input dimension, so it's within alpha and beta. So we can work it out. I'm sorry, because I'm so sorry because here this is already taking that factor outside. So the kernel inside, I'm already taking the x and y outside, so the kernel inside is gonna be here alpha squared plus beta squared, and now we have the double part, so it's gonna be minus j 2 pi over lambda c, and now we have x alpha plus y beta, and now remember that our beta is gonna be on the dark red color. So in Fraunhofer, we say that this Fraunhofer because this is gonna be equal to 1. So we are assuming that we are in the extension of the object is so much smaller than the distance. So that's gonna be approximated to 1, and therefore under this approximation the whole integral is this right here is the Fourier transform kernel, where now our frequencies are gonna be u is gonna be x over lambda c, and our frequency b is gonna be the same, it's gonna be y over lambda c. So this is the Fourier transform of your object transmittance u and b, but remember that we said that u and b are related with xy and then your distance, right? Your wavelength and the distance between your input and then when you are observing. But clearly you're gonna see that this is a scale version of your Fourier transform. So the answer is true. So yes, the diffraction patterns of an object are a scale copy of its Fourier transform under Fraunhofer approximation. Alright, so the second problem is, which is gonna be number 8, it's gonna be like, consider that you have a forest system, right? And this is your object, and that's gonna be your output. And they ask us what is gonna be the filter that you have used to obtain the image. Alright, so this is like the object becomes like 2 sinusoidal. So this is gonna be 1 sinusoidal. So this is kind of like the representation that we have. Sorry, I don't want to. So this is gonna be 1 sinusoidal along the x component, right? And then we're gonna have other sinusoidals along the y. But if we analyze the spectrum, when we have cosines or sines, the spectrum is gonna become 2 deltas, 2 impulses. So here we're gonna have the impulses along the y direction, which then is gonna be and then we're gonna have our impulses along our x direction. And theoretically, they need to be the same distance, because you see like the periods are gonna be the same. So this is gonna be our sample. So this is our object transformation, and that is gonna get multiplied, right, with our filter. That this is what we need to figure it out. What is gonna be our filter? So our image at the end, it's all black. We don't have nothing on the image, right? So clearly what we need to have is, we need to have a really low pass filter, so none of the impulses is gonna go. So our unknown is gonna become a low pass filter. So that's gonna become our answer number C. Think about it like our filter of A, this is gonna be a high pass filter. Sorry again. This is a high pass filter. So we are allowing to pass pretty much everything, or pretty much no filter. It's just a unity. So we will let it be our impulses. So we're gonna have our object is gonna look like our image, and then the other filter, we are only allowing to pass the impulses along the vertical direction in the Fourier domain. So here the output of that one will be our horizontal pattern. So that's another way of thinking about these problems. Like, if you are not for sure if it's C, just try to figure out if the other ones might be or not. So the third problem is that they want you to you are hired to build a system that works in Fraunhofer approximation, right? And they are telling you that the wavelength that you are using is 598 nanometers. So remember, that's gonna be 598 10 minus 9 meters. And they are assuming that the maximum lateral extent of your input is gonna be 2 centimeters. So I'm putting everything into the international system. So I'm putting everything in meters. And they ask us how far. So you know here that this is gonna be your maximum, right? And now you need to figure out how far you need to be so you can get the diffraction pattern, right? So if it's a circle, for example, here we're gonna have our sinc function. So the Fraunhofer approximation tells us that the distance c needs to be much larger than pi and then d squared over lambda, right? So if we know d, so we already know d, right? The problem is telling us that the maximum extent of the input is gonna be 2 centimeters. We already know lambda, 589 power minus 9 meters. So we just need to plug the numbers, and we're gonna know that c needs to be bigger than 21,000 2,133.5 meters, right? And they're asking you in terms of football fields. So one football field is around 91 meters. So that's gonna be that your c needs to be bigger than 23 football fields. And that means much more bigger. So that means at least 1 order of magnitude. So as a minimum 230. So A, B, and C definitely are smaller. So our only answer is that the distance needs to be 300 football field, and then we're gonna be able to do it, to be on the Fraunhofer approximation. Finally, the last problem is again another true and false. So they give us the input and output of a system. The system, we don't know anything about the system, right? But we know that the output, if you cannot see what it's clearly seen from the output are the edges. Every time that you see the edges of an object, that means that we are seeing the high pass frequency. So that means that our filter, right, it needs to block the low pass frequencies, and then we are passing our half frequency. Or if we want to see this kind of like in 1D, so each of you, right, in 1D dimension, that means that we have maximum, then we cannot block, and then we have maximum again. So we are kind of eliminating the low pass frequency. So they are saying the output image is obtained when the input image passes through a system with low pass filter. No, that is false, because we are saying that what we see is the high pass filter, right? So it passes for a low pass filter. I'm only allowing to pass the low pass frequencies and not the high. So that is false. And this low pass filter needs to be a high pass filter. Well, I hope that this is helpful and you know more now about Fourier optics. Thank you.